Hello everyone, I am Deepak Paliwal. So, in the continuation of the previous lecture, today we will discuss about various important characteristics of dislocations. Okay, so the first one, termination. Dislocation always terminates at the surface. Like dislocation never terminate within the material or within the crystal. It always terminate at the surface, or it will form branches, or it will terminate at the grain boundary. At the grain boundaries, or it will get form a loop. We will discuss about various dislocation loop like glide loop, prismatic loops. So, from this first point, we can understand that the termination of the dislocation never happens within the crystal or the within the material. It always terminate at the surface, or it will form branch, or it will terminate at the grain boundary, or it will form loops. And various dislocation loops like glide loop and prismatic loops will form. The second characteristics is the line direction of Berger vector, line direction of dislocation. Sorry, I was calling like Berger vector. So the line direction of the dislocation can change, but Berger vector direction remains constant. What I am saying, like, suppose we have a dislocation loop like this. So the Berger vector direction, suppose I have Berger vector direction is like this, and line vector, we know line vector is tangent vector to dislocation line. Okay, so like if I draw, this is the direction, this is the direction. Okay, if I draw the tangent, this is the line vector. If I draw tangent here, this is the line vector. If I draw the tangent here, then this is the line vector. But the everywhere the Berger vector direction is, let me have some different color here. Okay, okay, this is perfect. So this is Berger vector. Here Berger vector is same. Here Berger vector is like this. Here Berger vector is like this. So the Berger vector direction remains constant. Berger vector direction remains constant, but the line direction of the dislocation can change. Okay. Again, the third rule is the Berger vector remains conserved. Berger vector remains conserved. What does it mean? Like, suppose a Berger vector, okay, it will dissociate into the two parcels b1 and b2. If I add b1 and b2, again I will get Berger vector b. So there is a rule of conservation of the Berger vector. So the Berger vector remains conserved. So why this kind of splitting will happen? In what condition this kind of splitting will happen? This we will learn in the upcoming lecture series. But for this point of time, the Berger vector remains conserved. This is the important characteristics of any dislocation. Okay. Again, at node at node, summation of all the Berger vector remains 0. Suppose we have b1, b2, b3. Okay, here b1 is coming, b1 is coming, b2 is going, b3 is coming. Okay, if I take b1, suppose I am taking sign convention, the Berger vector direction towards the node point is positive, and this is negative. the the Berger vector going away from the node point is negative. So if I sum b1 plus b3 minus b2, it will give 0. So this is the important characteristics that, like, the summation of the Berger vector at the node point will give 0 value. Okay, now here I have mentioned about the loops. So let us understand what is loops. As we know, the dislocations form loops. Dislocations form loop. So there are mainly two type of loop. One is glide loop, another one is prismatic loop. So the important characteristics of the glide loop, like, we have loop like this. Okay, it has both screw and edge dislocation. Like, this is the Berger vector direction and this is the loop direction. Okay, so like, let me draw the tangent vector. Here we have tangent, here we have tangent, here we have tangent, here we have tangent. So this kind of loop is known as the glide loop, in which both screw dislocation and edge dislocations are present. How I can say the screw dislocation and edge dislocation is present? Look at, let me mark this with number 1, 2, 3, 4. So at the position 1, Berger vector b1 and the tangent vector u1 are perpendicular. So this is the edge dislocation. If you observe the position 2, the b1 vector is parallel to the u, let me call it u2 vector. So this is your screw dislocation. Again, one more important characteristics here is, like, at particular points, character of dislocations are screw or edge. Otherwise क्या है? Otherwise it is mixed dislocation. Mixed dislocations are the dislocations which has both character screw as well as edge. Okay, another loop is your prismatic loop. Prismatic loop is important because it has only one character, that is edge character. So how this kind of loop is forming? Suppose if you have loop, okay, and your Berger vector is perpendicular or in the direction of a plane normal, or a normal to this plane of paper. So if your Berger vector is like this, so wherever you draw, suppose this is the direction of loop, anywhere if you draw the tangent vector, the Berger vector is always perpendicular. That means this loop has only edge character. Okay, so this loop has only edge character. So in this kind of loop, two type of loops can be possible. One in which the planes or partial planes are outwards, or planes are inward. What does it mean? Suppose all these plane are outward. Okay, in a similar fashion, if I draw like this, Berger vector is along the plane normal or the normal to this plane of paper, and all the loops are, all the partial planes becomes inward, then it is the inward prismatic loop, this is the outward prismatic loop. Okay, again like suppose we have dislocation like line like this, and it has Berger vector this. So what we can do first method, say we can, and this is the tangent. Okay, so what we can do, we can take component of Berger vector along line vector and perpendicular to line vector. So I can take the component like this is Berger vector's cos component, this is Berger vector sine component. Okay, the second method for this kind of mixed dislocation, what we can do, like this is our Berger vector, this is our line vector. What we can do, we can take component of your line vector along the Berger vector. So this become u cos theta, and this become u sin theta. So the line vector along Berger vector develops a dislocation called screw in nature, and perpendicular to Berger vector develops a dislocation of edge in character. Okay, so here we have understand about the various characteristics. In briefly, if I say, the termination of dislocation never happens inside the crystal. The line direction of any dislocation can vary, but the Berger vector direction remains constant. Berger vector magnitude remains conserved, whether it is splitting of Berger vector into two Berger vector, but if we take the sum, then it will come to the original Berger vector. And at the node, when we do sum of all the Berger vector, it will comes to the 0. Then we have talked about the various loops. One is the glide loop, another one is the prismatic loop. In the glide loop, both the edge dislocation and the screw dislocation characteristics are present, and only at some specific points we have edge character and the screw character. And in the prismatic loop, we have only edge character, in which two type of conditions are possible, one where the planes are outward and another one the planes are inward. And then we have talk about the mixed type of dislocation, how to find out the Berger vector and the line vector. So there are the two methods. First method, we can take the component of the Berger vector along the line vector and perpendicular to the line vector, and in the second method we can decompose, or we can take component of the line vector along the Berger vector and perpendicular to the Berger vector. So the components which are along the Berger vector, it will develop a dislocation which has nature of screw dislocation, and the Berger vector which is perpendicular to the line component which is perpendicular to the Berger vector, it will develop edge type character. Okay, so in the next lecture we will talk about the strain fields which are present around the dislocations, and how we can calculate, how we can evaluate the strain field, and what will be the nature of these strain fields, that we will discuss in the next lecture. Till then, bye bye. Thank you for watching the videos. Thank you.